Alright, in this video we're going to be looking at the central limit theorem, and we're going to be applying the central limit theorem to find probabilities. Okay, so now let's look at what the central limit theorem states. Okay, so here we have the central limit theorem, and according to the central limit theorem, you have to have this: the original population can have any distribution and it can be a skewed distribution or a uniform distribution and so on. But the distribution can be approximated by a normal distribution when n, that's your sample size, is bigger than 30. Okay? So if you have a sample size bigger than 30, then that means that our original population can be approximated by a normal distribution. Okay? Now, there are a couple of cases that you have to have. One is this: if you plan on using the central limit theorem, one is this: the original population must be normally distributed. And that's regardless of the sample size. Okay? Because you have to be told that your original population is normally distributed. And second, the sample size, which is your n, is greater than 30. Okay? One of those two cases must be met for you to apply the central limit theorem. If you don't have a population that's normally distributed, and if your sample size is less than 30, then that means, less than or equal to 30, then that means you cannot apply the central limit theorem. You have to use other methods. Okay, now, and I'm also going to give you the z-score conversion, because this one is a little bit different from the z-score that you use. So your z-score conversion is going to be this, and that's of x bar, and that's this: z is equal to x bar minus mu. This is divided by sigma over the square root of n. Okay. Your x bar is your sample mean, mu is the population mean, and sigma over n, that represents the standard deviation of all of your sample means. Sigma divided by the square root of n represents the standard deviation of all the values of x bar. Okay. Now, when we go ahead and solve problems, like the ones that we're going to be doing a little bit later, if you are dealing with an individual value, and what do I mean by individual value? That means that n is equal to 1. Then we use this formula. Z is equal to x minus mu divided by sigma. Just an individual value. So we use the x value minus mu divided by sigma. So that formula is correct. We've been using that in one of the videos when we were doing the applications of a normal distribution. Okay. Now, for a mean from a sample of values, that's where your sample size is bigger than 1, then you're going to use this formula. Z is equal to, this time, x bar minus mu divided by sigma over the square root of n. Okay, that we just got through talking about. Because we're dealing with a mean from a sample of values. Okay. So let's look at a few examples of just this. Let's start with something like this. Assume that women's heights are normally distributed with a mean given by mu is equal to 63.2 and a standard deviation given by sigma is equal to 2.7 inches. Now in this case, we want to do parts A and B. And part A is this. If one woman is randomly selected, find the probability that her height is less than 64 inches. Okay, so here we want to draw a normal curve. Okay. Okay, so here we're drawing a normal curve. We're dealing with a normal distribution. So we draw a normal curve. In this case, your mu is 63.2 inches, and sigma, which is your standard deviation, is 2.7. And 64 inches is to the right of 63. So here's 64 here. And we're dealing with the height less than 64. So we're going to shade the area to the left of that boundary of 64. Okay. Alright, so now we're dealing with n is equal to 1, a single woman. So what we want to do is convert that 64 to a z-score using the formula z is equal to x minus mu divided by sigma. So in this case here, your x is, in this case, that's your 64. So it'll be 64 minus 63.2 divided by sigma, which is 2.7. Okay, now if you were to type all this in the calculator, like I'm going to do right here, the numerator will be in parentheses, so you have 64 minus 63.2, close parentheses, divided by 2.7. You'll get 0.30 if you want to round this off to 3 decimal places. So your z value is 0.30. Now if you recall, you have to use your standard normal distribution table, or for those of you who are taking my online class, you know it's table A-2. So in this case here, we find 0.03, 0.03, and then 0.00. So we read across to 0.3 and 00 will get 0.6179. So that area to the left that's in green, which is what we want, is 0.6179. So the probability that a single woman randomly selected that her height will be less than 64 inches will be 0.6179. Alright, so that's part B. Part A. Now part B is this. If 35 women are randomly selected, find the probability that they have a mean height less than 64 inches. Okay, so now this is going to be for N equaling the 35. So now we're going to convert that to a z-score. This time we're going to use a different formula. Z is equal to x bar minus mu divided by sigma over the square root of n. Okay, so we're dealing with someone having a mean height less than 64 inches. So now your x bar, which is your mean height, that's 64, minus mu, which was 63.2, divided by sigma, that's 2.7, divided by the square root of n, and n is 35. Now, if we enter this in the calculator, this numerator has to be in parentheses. Not only that, your denominator has to be in parentheses as well. So, here we go. Using the calculator, left parentheses, the numerator, which is 64, minus 63.2, close parentheses, divided by, and then left parentheses, the square root second x squared. I'm sorry. Let me delete that. In this case here, you get 2.7 divided by, and now second x squared for the square root, and then 35. Close the parentheses around the 35, and then close it again, because we opened the parentheses in front of the 2.7, and then hit enter. So now that z value to two decimal places is now 1.75. Okay. So we're dealing with 35 women randomly selected. Okay. Now that z value is 1.75. Now, it is a positive z-score, so we pull up our standard normal distribution table and find 1.75. Well, 1.7 is right here, and then 0.05 is this column right here. So we read across 1.7, and then 0.05 will be 0.9599. So in this case here, your probability that 35 randomly selected women will have a mean height. Now notice I'm putting the x bar here instead of x less than 64. That would be 0.9599. So in this case, we're dealing with a mean height, so that's why I put x bar here when I wrote this. Okay. Alright, let's do another example. The overhead reach distances of adult females are normally distributed with a mean of 205.5 centimeters and a standard deviation of 8.9 centimeters. Part A is this: find the probability that an individual distance is greater than 214.80 centimeters. So this is going to be part A, and it would help to draw the normal curve to see what's going on. In this case, your mean is 205.5, and the standard deviation is 8.9. And we're dealing with 214.80, which is to the right of 205.5. And we're dealing with a distance greater than. So in this case, it's this area to the right. Well, we're finding the area to the right, and we know our table gives us the cumulative area from the left. That means we have to do 1 minus that area to get this cumulative area to the right. Okay, so in this case here, we're dealing with an individual distance, so that means your n is equal to 1. So we convert that to a z-score using z is equal to x minus mu divided by sigma. In this case, your x value in question is 214.80 minus mu, which is 205.5, divided by sigma, which is 8.9. So that means that your z-score, if you do 214.80 minus 205, whatever that is, divide that by 8.9, you're going to get 1.04. And we always round the z-scores to 2 decimal places, if you recall. Now, we're going to use that 1.04 to find the area to the left, but we want the area to the right. Now, 1.04, here's 1.0, and then 0.04 is this column here. So go to the right and down on the row in the column, you'll see is 0.8508. 0.8508. So in this case here, this is the area to the left. But we want the area to the right. So we first got to do 1 minus 0.8508 to get 0.1492. That's this shaded area in green. So the probability that an individual distance is greater than 214.80 would be 0.1492. Alright, now in part B it says here, find the probability that the mean for 15 randomly selected distances is greater than 203.30 centimeters. Okay, so now, in this case, I know I'm going to have to draw another normal curve because that x value has changed. Our mean is 205.5. Standard deviation is 8.9. And we're saying that 203.30, actually 203.30 will be on the left-hand side. And we're dealing with greater than, so it's got to be the shaded area to the right. So again, we're going to be doing 1 minus the cumulative area from the left to get that cumulative area from the right. And 203.30 is on the left-hand side. So now, with n equaling to 15, your z value is going to be this. This time, x bar is at 203.30 minus your mu, which is 205.5, divided by sigma, which is 8.9. And that's over the square root of n, which is 15. So in this case here, to find out what your z is, using the calculator, we put this in parentheses and this in parentheses as well. And I'll go ahead and show you how that's done. Left parentheses, 203.30 minus 205.5, close parentheses, divided by, and then open parentheses, 8.9 divided by, and then second x squared, 15. Close the parentheses around the 15, close it again because we open it when we, from the very beginning, and then hit enter. This will be, in this case, negative 0.96. Our z value, we rounded 2 decimal places, so here this will be a negative 0.96. And then we pull up our table to find negative 0.96. Okay, negative 0.9 is over here. And this column right here represents 0.06. So read across to negative 0.09 and down to 0.06, it will be 0.3685. I'm sorry. No, 0.1685. Here we go. Yeah, 0.1685. But that's this area to the left, 0.1685. We want the area to the right. So we got to do 1 minus 0.1685, which would give us 0.8315. Okay, so that's going to represent the probability that the mean of 15 randomly selected distances is greater than 203.30 centimeters. That would be 0.8315. Okay. There we go. 0.8315. Okay. And part C, why can the normal distribution be used in part B even though the sample size does not exceed 30? So that's part C. Now, when you read this problem, it does tell you that the overhead reach distance of adult females are normally distributed. So that's one of the requirements for applying the central limit theorem, is that you have to have a normal distribution. So here we can say that the overhead reach distances of adult females are normally distributed. And the overhead reach distances of adult females are normally distributed, which is why the normal distribution can be used. Okay, let me do one more for this video. Alright, let's say we had this. A certain brand of candies have a mean weight of 0.8578 grams and a standard deviation of 0.0514, based on a sample of a package containing 467 candies. The package label stated that the net weight is 398.6 grams. If every package has 467 candies, the mean weight of the candies must exceed 398.6 over 467 or 0.8535 for the net contents to weigh at least 398.6 grams. So here we got two parts. Well, actually 3 parts. If one candy is randomly selected, find the probability that it weighs more than 0.85 grams. Okay, so let's look at part A. And it helps to draw a normal curve. In this case, your mu is 0.8578. Standard deviation was 0.00514. And in this case, 0.8535, that's a value on the left-hand side of 0.8578. And we're dealing with greater than, so we're dealing with the area to the right. Okay, so we just shade this area to the right that's in green. Okay, so now we're dealing with one candy randomly selected. That's your n is equal to 1. So of course we convert that to a z-score using x minus mu divided by sigma, which is in this case x, which is 0.8535 minus mu, which is 0.8578, and all that's divided by sigma, which is 0.0514. And I think I got one too many zeros here. So that'll be 0.0514. Okay. Of course, you can put this in parentheses. Do this on the calculator. You'll see that it'll come up with negative 0.08 as your z value. And now you want to convert that to a probability value. So in this case here, it's a negative z-score. So we find negative 0.0, which is way down here at the bottom, and then 0.8 is this column down here. So if you read to the right and down 0.08, you're going to get 0.4681. But that 0.4681 is this area to the left. We want the area to the right. So the area to the right is this 1 minus that 0.4681, which will be 0.5319. So in this case here, the probability, if a single candy is randomly selected, that it weighs more than 0.8535 grams, that probability would be 0.5319. Okay, so that's part A. Right, now part B. We're dealing with 467 candies. They're randomly selected. So you want to find the probability that their mean weight is at least 0.8535 grams. Okay, so now we have to use the z formula of x bar minus mu divided by sigma over the square root of n. Now here in this case, your x bar this time is now 0.8535 minus mu, which is 0.8578. That's divided by sigma, which is 0.0514. That's going to be divided by the square root of n, and n is 467. Okay, and as you know, this needs to be in parentheses, and this also needs to be in parentheses. Okay, so now, using the calculator, left parentheses, 0.8535 minus 0.8578, close parentheses, divided by left parentheses, 0.0514 divided by second x squared for the square root, and then 467, close your parentheses twice, and then hit enter. To two decimal places, that would be negative 1.81. Okay, and then we find negative 1.81 on our negative z-score for the standard normal distribution. So here we got negative 1.8, which is right here, and then 0.01 is this column right here. So read across and down, you'll see that is 0.0351. But keep in mind, 0.0351 represents the area to the left. We want the area to the right. So the area to the right would be 1 minus 0.0351, which will be 0.9649. Okay. Now again, you can draw the normal curve if you want to, but in this case here, think about it, that 0.0351 will be your area to the left. You're still finding the shaded area to the right. See, that's why you still have to do 1 minus 0.0351. So the probability that the mean, that 467 candies have a mean weight of at least 0.8535 grams, that probability there will be 0.9649. Okay. Okay, so this should be enough to assist you with some of the homework problems for the central limit theorem, and that will complete this video.